Good day, everyone. We're going to start topic number 2 in today's lesson. This topic is something called functions. Functions are a special kind of a relationship in mathematics. A relationship exists where one set of numbers somehow influences another set of numbers. Think of it as an equation, for example, but there's various ways you can write relations. Equations is just one way. If you have a simple equation such as y equals 3x plus 1. Now you can see, you've seen equations like this before. This is a simple linear equation. The y is what we call the dependent variable. Usually in an equation, if you write it down, the variable that's by itself on the left-hand side is what we call the dependent variable. In most cases, that would be your y. All the possible values of that dependent variable, that's what we call the range of the relation, or it could be the range of the function if it's a function. The second quantity, in this case the x, the independent variable, is what we call that. And all the possible values of the independent variable is what we call the domain of the function or the relation. All right, so we're going to be looking at domain. There's domain right there. We're going to be looking at domain and range in a little more detail. Now, how can you tell if a relation is a function or not? Well, there's a certain thing that has to be true, and it's stated right here. All right, there's how you can tell if something is a function or not. For each value of the independent variable, and usually that's the x's again, there should only be one value of the dependent variable, which in this case is the y's. All right, so it's kind of like saying this. If you have a relation where x is equal to 1 and y is equal to 3, but if in that same relation x is equal to 1 and y is equal to 4, now this would not represent a function. It is still a relation, but it's not a function, because one value of the independent variable, x, gave you more than one value of the dependent variable, which is y. All right, so that's how you can recognize if something is a function or not. So we're going to be looking at a function in various forms. We're going to be looking at equations, tables of values, which is the same as points, really, and also by looking at a graph. How can we recognize if something is a function or not? So let's look at example number 1 here on the bottom of page 2. What is this asking us to do? Well, it's saying to rearrange each equation to find the function, if it's possible, that is, and state the independent and the dependent variables. Now, some of these equations, you can write them two ways, all right? And in that case, the dependent and independent variables would be different. So let's look at A, for example, right here. Is it possible to take this equation and rewrite it so that y is by itself? Yeah, I think we can do that fairly easily. That doesn't look like a big task. So if we write the 2y first, we'll bring the 6x to the other side, and it becomes a minus 6x plus 16. And now divide everything by 2, and you're going to get y is equal to negative 3x plus 8. All right, and you probably recognize that as another simple linear equation. Well, if you write it in this form, y is the dependent variable because it's by itself on the left-hand side. This is definitely a function, and x, in this case, is the independent variable. All right? So we say that this is written as a function of x. This equation, this relation, is written as a function of x. That would mean that the x is the independent variable. Now, can we write it as a function of y? In other words, can we get the x by itself in this example? Well, let's try it. Let's see if we can do that. Because if we can, that would also represent a function, but we would have a changing of the dependent and the independent variables. All right, so let's just try that. Let's see if we can do that. I would leave the 6x by itself equals negative 2y plus 16. Divide everything by 6, all the terms by 6, and just reduce them as much as you can. You can leave them as fractions if you want. So x is equal to negative 1/3 y That reduces. And 16 over 6 would reduce to 8 over 3. There you go. That's also a function. But this, we say, is a function of y. Y is now the independent variable because of the way we've written the equation. And x is actually the dependent variable in this case. All right, so we were able to take that first one and write it in two different ways. Okay, now let's have a look at B. B is slightly different. Now, the first question you might want to ask yourself is, can I take that equation? Can I take this relation right here? Can I write this as a function of x? In other words, can I get the y by itself on the left-hand side and have it as the dependent variable? And I think we can pretty much do that easily enough. So let me see. You leave the negative y by itself. Bring that 2x squared to the right-hand side. And of course, it becomes a negative 2x squared. Combine that with the 4x squared that's already there, and you're going to end up with 2x squared plus 3x plus 10. Now, remember, you have to get rid of that negative as well there in front of the y. So if you multiply both sides by -1, or think of it as dividing everything by -1, whichever way you want to look at that, you're going to end up with y is equal to negative 2x squared minus 3x minus 10. And that's a function. All right, that is definitely a function. In fact, we say that this relation is a function of x because x is now, let me just write it over here, x is the independent variable. All right, now y, because the y is written by itself on the left-hand side, y is what we call the dependent variable. Okay, pretty good. Now, what would happen if you tried to get the x by itself? Is it possible to write this relation as a function of y? Well, let me see. What would happen if you tried to get the x by itself? Now, notice you have x squareds there, and you also have x's. It is possible to get the x by itself, but if you do so, you'd have to use a technique called completing the square. You may be familiar with that from your Math 1700. But if you did that, somewhere on the right-hand side, you'd end up with a plus or minus, all right? And that would certainly indicate that it is not a function. Getting the x by itself here would just leave you with a mess. So what we say is that this relation cannot be written as a function. This pen I'm using is not very good. Cannot be written as a function of y. In other words, you cannot write it with y being the independent variable. All right, so that's what we would say there. Now, I'll leave C and D for you to try, and also practice number 1 on the next page. You can try those as well. They're all relatively straightforward. Make sure you check the solutions in D2L as you do these. And now we're going to look at, on page 3, this is a table of values. How can you tell by looking at a table of values if the relation represents a function or not? Well, it goes back to the definition of what a function is. Remember what we said a function was. 1x, or the independent variable, usually that's x, can only give you back one value of the dependent variable, and that in most cases is y. Well, if you look at this table right here on the left-hand side, if I said to you x is equal to -1, what is the y value? What possible values of y are there? Well, you'd have to reply with two different y values. You'd have to say that y could be -2, and that's represented by this point right there, or y is equal to +10. All right, you see that? One x value gives you two different y values. So this table of values here is not a function. It's definitely not. Even if you saw it written as points, for example, -1, -2, all right, you see your x and your y, but also -1, 10, you see that? that would also indicate it's not a function because one x value gives you two different y values. Now, if you look at this table, the second one over on the right-hand side, if I said to you x is equal to -2, what is y? Well, you'd have to say 3. There's only one possible y value. If I said to you x is equal to -1, what is y? You'd say 4. There's only one possible y value. And that's true for all of these x values right there. So this table of values does indeed represent a function. Every single x has only one y associated with it. Now, what about graphs? I'm going to let you try the practice ones down below that, practice number 2. That's relatively straightforward. But I want to point out what would happen to the graphs. What if I took those 2 points right here, and what if I actually plotted them on a set of axes? Well, let's see what would happen. I'll just draw a rough graph right here, just to show you. -1, -2 would be approximately right there somewhere. Something like that, okay? 1 to the left and 2 down. But -1, 10 would also be 1 to the left, but 10 up, way up there somewhere. Now, if you look at those 2 points, do you notice that one of them is directly above the other? In other words, if I can draw this fairly accurately, let me see. In other words, those 2 points lie on the same vertical line. That's a clue. If you're looking at a graph and you're trying to determine if it's a function or not, ask yourself, is there anywhere on that graph where 2 points are one right above the other, or do they lie on the same vertical line? And for graphs, that leads us to something, a very simple test actually, called the vertical line test. Ta-da! There it is on page 4. Look at that, the vertical line test. Take your graph, look at your graph. Just imagine that you can draw a vertical line wherever you want, anywhere, cutting through your graph, cutting through your curve or cutting through your line. If that vertical line intersects the curve or line in more than one place, then it is not a function. So it's a really simple test that you can perform. And I mean, there's no workings required to this. So example number 3, this is on page 4. Perform the vertical line test to determine if the graph represents a function. Well, let's look at A. Let's look at A. Now, if you could imagine drawing vertical lines wherever you wanted to. Here's a vertical line, for example. We'll pretend it's vertical. How many places does that intersect the curve? Well, only once, right there. Here's another vertical line. That intersects the curve only once, right there. Here's another vertical line. Intersects the curve in only one spot, right there. So this graph does represent a function. No matter where you draw your vertical line, it will only intersect the graph in one place. Now, the reason for it being a function, if you were asked on a test or on a quiz to justify your answer, you would say because this graph passes the, excuse me, passes the vertical line test. Okay, let's look at B. Okay, can you draw a vertical line here that would intersect this curve? That's actually an ellipse by the looks of it. Can you draw a vertical line that would intersect this curve in more than one place? And yeah, actually, there's like an infinite number of vertical lines that you could draw. Here's one, for example. It intersects the curve once there and once there. You see that? That represents 2 points, one right above the other. In other words, the same x value, but 2 different y values. So we would say that this graph is not a function. It does not represent a function. And again, if you had to justify your answer, why is it not a function? You would say because it fails the vertical line test. All right, so it's a very simple test that you can perform. Okay, we're almost out of time. I would like for you also to try practice number 3. On the bottom of page 4, it looks pretty simple. It's relatively straightforward. Don't forget to keep checking your answers in D2L. If you have any problems with any of this, please make sure you pop me an email, and I'll certainly get back to you. Okay, so that's it for today's lesson. We're almost out of time, and I'll see you again later. Bye-bye.